Hello everyone, welcome to the GGM YouTube channel, and today we will be doing stars and bars. So last week, if you remember, we did some combinatorics, we did a sort of introduction, we did combinations and permutations. This week we'll be doing some more advanced combinatorics problem solving techniques, and this will be stars and bars. So just as a review from last week, we're going to look at permutations with repetition before we get to combinations with repetition. So let's say we have a combination lock, which again should be called a permutation lock, with 5 slots. Each slot can have a number 0 to 9. How many permutations are possible? I'll give you 5 seconds. Okay, so this problem should be fairly straightforward. Each slot can have a number from 0 to 9, so those are 10 possibilities per slot. So we have 10 to the 5th as our answer. And you should always check the context of the problem to see if there's replacement or not. So with replacement, it basically means if something has replacement, that means you can have multiple of the same thing in the answer, right? So this one has replacement because, for example, we can have 2 zeros or like 3 nines or something. But if it's without replacement, that means that we can't have multiple of the same number in an answer. So then we can only have one of each number, right? So if the resulting permutations must have distinct objects, it's without repetition. But if it allows more than one, then it is with repetition. One more thing. So let's say we want to find the number of rearrangements of the word Toronto. The answer is not just 7 factorial, because if we used our strategy of 7 possible letters for the first letter, and then 6 for the next one, we're going to overcount. And this is because Toronto has 3 O's and 2 T's. And since these letters are identical to each other, for every rearrangement of Toronto, because we're treating these 3 O's and 2 T's as different letters, even though they're actually the same letter, we're counting it 3 factorial times 2 factorial times more than we should be, because there's 3 factorial times to rearrange the O's and 2 factorial ways to rearrange the T's. So our answer is 7 factorial divided by 3 factorial times 2 factorial. Help you visualize this. We're going to have what? T-O Toronto, right? So we have 3 O's and we have 2 T's. And so let's just suppose that the O's are actually all different. So O1, O2, O3, and the T's are different, so T1, T2. Okay, great. So now, right, for a rearrangement of this new word, right, T01, T1, like this, right? If we rearrange this, we're going to have 7 factorial possibilities, right? Because, again, we have 7 distinct choices for the first letter, and then 6 for the next one, right? So it's just going to keep going down, right? But now, the thing is that there's 3 factorial ways to rearrange the O's, right? And there's 2 factorial ways to rearrange the T's. And the issue with that is that if we have some arrangement of O's, for example, O1, O2, O3, these are all actually, if I have O2, O3, O1, for example, these two are the same arrangement because the O's are all the same, but we're treating them as if they were different. So for every 3 arrangement of Toronto, we need to divide by 3 factorial. Because otherwise, we're going to be treating 3 factorial permutations of identical O's as different when they're actually the same. And the same logic goes for the T's. So the answer is going to be 7 factorial divided by 3 factorial times 2 factorial. Because for each arrangement of Toronto, we're counting it this many times more than we should be. So then we're dividing it to get our actual answer. So if we actually want to find out what that is, we have 7 factorial is equal to 5040. And then we're going to divide by 3 factorial is 6. So this is 6 times 2, that's 12. And that should come out to about 420. So that should be our answer here, 420. So this is just sort of something that you have to watch out for when you're doing permutations. Make sure you always divide out the identical objects. You have to find how many ways there are to permute those identical objects and then just divide the total by it. So combinations with repetition is called stars and bars. That's how you solve these types of problems. So this is the hardest type of problem out of the bunch, or out of what we've already discussed. So let's say you're buying ice cream cones for a party, right? So you have 3 different types of ice cream labeled A, B, and C. And let's say you want to get 5 ice cream cones. How many different combinations of ice cream cones can you have? So this problem is slightly different from the things that we've done before, right? Because we can have 2 cones of ice cream A and 3 cones of ice cream B, or like 5 cones of ice cream B, and so on, right? You can have multiple cones of the same ice cream, which is the reason where, well, if you try to apply what we've already learned to this problem, you're going to run into some problems. So the key to this problem is to use what's called the stars and bars method. It's also called ball and urns, or cookies and kids. So there's many names for this, but I think stars and bars is generally the one that's the most used. So we will represent ice cream cones as quote-unquote stars or dots. And since there are 5 cones, we have 5 stars. So now we have to figure out how to divide these 5 stars into quote-unquote bins or groups, right? So since there's 3 types of ice cream, we'll have 3 bins. And now our question is, how do we divide these 5 cones into these 3 groups? So we have our 5 stars and our 3 bins, and the stars are represented below. They're just dots, basically. And now we need something to split these 5 stars into 3 groups. And this is where our quote-unquote bars come in. These are the dividers, essentially. So as you can see, we have 2 bars splitting the stars into 3 groups. And each group represents a type of ice cream. So we can say that the first group, before the first divider, is ice cream A. So that's 1 star, so there's 1 scoop. The second group is ice cream B, between those 2 bars, so that's 2 scoops. And the third group is ice cream C, which is also 2 scoops, and that's behind the second bar. And there will always be 1 less bar than the number of groups. So if we have 7 stars being split into 4 groups, we will use 3 bars, right? Hopefully that makes sense. You need n groups, so you divide with n minus 1 bars, because you can have n minus 1 groups before each of those bars, and then 1 group after. So this is generally how stars and bars works. So let's look at our initial 5 stars again. How many ways are there to add the first bar in? How many ways can we take the first bar and insert it in between these stars, or around the edges? So there are 6 ways to add this first bar in, because there is the empty space in front of the first star, because you can have none of ice cream A, for example. There's the empty space in front of the second star, and then empty space in front of the next star, and then so on. Right? So there's 4 empty spaces in between the stars, and there's also an empty space after the last star. So to visualize this better, we can have our 5 stars, right? And we can have it before the first star, in between these 2, in between these 2, in between these 2, in between these 2, and at the last here. So we have 6 places that we can put our bar. So let's just put our first bar here. I don't know, right? It could be any of these 6 places. So now the question becomes, how many ways to add our second bar in? And now, right, we have 7 ways because we first have our 5 stars and then our bar, right, because we have our first bar in there already. So we have the first and the last space, as well as the 5 empty spaces between the stars and also between the stars and first bar. So going back to this, let's say we have our arrangement again. So we've added our first bar in, now we want to figure out how do we add our second bar in. We can add it at the very beginning, in the middle of these two, then we can add it in the middle of this star and this bar, no issue with that. We can put it here between this bar and this star. We can put it in between these 2 stars and between these 2 stars, or at the very end. So we have 7 spaces. So you're going to notice the more bars we put in, the more options we actually have. So there are 7 ways to add the second bar in. And you'll notice we have 6 times 7 now ways to add these 2 bars in, right? But now we have to divide by 2 because the bars are indistinguishable, they're identical, right? So we need to divide out the identical things. So that just gives us 21. So that's actually the answer to our stars and bars problem here, 21 ways to split this ice cream into 3 groups. Now, because there are 6 ways to add the first bar in and 7 ways to add the second bar in, we do 6 times 7 divided by 2 factorial, right? Because there's 2 factorial ways to rearrange these indistinguishable bars. So now let's say that we have the same problem, but this time you have to get at least 1 of each type of ice cream. So you have to have at least 1 of ice cream A, at least 1 of ice cream B, at least 1 of ice cream C. So how do you think we're going to do this problem? I'll give you 5 seconds to think about it. Alright. So let's look at our 5 stars again. Because every group or every type of ice cream must have at least 1 star, our first bar cannot be in the first or last position. Because if it's the first position, right, before the first star, that means ice cream A has no cones. And we can't have that, right? We already said each type has to have at least 1 star. And it can't be in the last because ice cream C won't have anything. So there's 4 empty spaces where it can go. Now there's 5 stars and a bar. And the second bar can't go in the first or last position, and it can't also cannot go between a star and a bar. And the reason is that if it goes between a star and a bar, there's 2 bars next to each other. So whatever group represents the group in between those bars, in this case it's ice cream B, it's going to have 0 cones. And again, we can't have that. So it has 3 places left, right? So we have 4 times 3 divided by 2 factorial equals 6 as our answer. So here's a better visualization of this. So instead of this, right, instead of this stuff, we're going to call this 0 allowed, right, because we can have 0 stars in a certain group. But now we're going to have another space, right, where 0 is not allowed. You have to have at least 1 star in each group. So here, you'll notice we cannot put them on the edges anymore. We can only put them in the middle. So we have 4 places for our first bar. And now, let's say I put the bar here or something, right? So you'll notice, first, I cannot put the next bar here because then ice cream B will not have anything in it. And I can't put it there. You want to avoid any situation where 2 bars are next to each other or there are bars on the edge. Because then ice cream will not have anything, right? One ice cream type will not have any cones. So we can insert it in between these 2 stars, in between these 2 stars, or in between these 2 stars. And remember, can't go on the edges, so we're done. And again, we have to divide by 2 because these are indistinguishable bars, right? So it's going to equal to 6. So in general, if n is the number of total items and k is the number of groups, the formula for stars and bars without restrictions is n plus k minus 1 choose k minus 1. And you can also rewrite this as n plus k minus 1 choose n. Remember the identity we learned last week, that n choose k is equal to n choose n minus k. But you're probably going to use the first one anyway, because n is usually bigger than k minus 1, so it's just more convenient. So this formula comes from the fact that k minus 1 is the number of bars, and there's n plus k minus 1 total places we can put the bars, and out of those places we're choosing k minus 1 of them. However, if we have to have at least one item in each group, then n minus k choose k minus, n minus 1 choose k minus 1 is the formula. And in total, there's n minus 1 gaps between the stars, and we're choosing k minus 1 of them to contain a bar. So just to explain why they work a little bit more, if we have at least one item in each bin, for the n items we have, there's only n minus 1 empty spaces in between those n items, right? So because if I have 7 stars, for example, I have 6 spaces in between those stars in total. So I have n minus 1 empty spaces, and out of those empty spaces, I have to put k minus 1 bars there. So we're just choosing k minus 1 spaces out of the n minus 1 spaces to contain a bar. And the no restrictions one, it might be a little bit harder to understand, but basically at the end, you have n plus k minus 1 items arranged in a line, right? Because k minus 1 is the number of bars, and at the end, not only will you have n stars, but you'll also have k minus 1 bars. So at the end, we're going to have n plus k minus 1 items. So that's the amount of empty spaces you're going to have to put your bars, right? And there's k minus 1 bars. So you take n plus k minus 1 spaces and you insert k minus 1 bars. Okay, so just to close off this video, here's 2 stars and bars problem to get you started with this concept. Harris has 20 apples, and he wants to distribute these among his 3 friends and himself, making 4 people in total. If he wants each person to get at least 1 apple, how many ways are there to distribute the apples? I'll give you 5 seconds. Okay. So this is just a straightforward direct application of one of the formulas. So we're going to look at the problem. We'll see, okay, so this is clearly combinatorics with repetition, right? Combinations, and well, it's each person has to get at least 1 apple, right? So we just use the formula where each person gets at least 1 thing, right? So we just do 20 minus 1 because 20 is n. We have n apples. We have 20 apples in total, right? 20 minus 1 choose 4 minus 1, right? Because we have 4 minus 1 bars. And that's 19 choose 3. And if you just calculate that out, you're going to get 969. Here's another problem. Ashley is taking balls for a juggling competition. She can use blue, red, green, or yellow balls. If she takes 10 balls, how many different combinations of balls can she take? So I'll give you another 5 seconds. Okay, so now she's allowed to not take any of a certain color, right? So it's not like she has to have at least 1 blue ball or something. She can have like all green balls, like we don't know. Maybe she really likes the color green, right? So we can just use the other formula, right? Because we have n balls, okay, so that's 10 balls in total, so 10 equals n. And we have k, well, we have 4 groups, so k equals 4. So we just do 10 plus 4 minus 1, choose 4 minus 1. and that's equal to 13 choose 3 equals 286. So that's how many combinations of balls she can take. And with that, we pretty much end off the video here. Next week, we're going to be doing something different with geometry. So this is pretty much the end of the video. You can look at the GGM newsletter if you want to find more about the subject. So yeah, thank you everyone. I'll see you next week.